Beautiful. Today we're going to do a little talking about, I want to finish a couple more examples of partial fractions, two things we haven't talked about, and then I'm going to give you time to work on your web work, start on the new web work that we have. If you don't have your laptop, I may have you covered. So, yeah, exactly. I aim to serve. I aim to please. Part of growing up with an emotionally unstable parent is just trying to please people all the time, right? So, and it turns out to work okay for the job that I'm in. So I just wanted to show you something real quick here. This is for another class that I'm teaching. This was made by a high school student who I worked with, I don't know, God, like a decade ago. He was looking for a math project for a science fair. So we came up with this. This is a Zeeman catastrophe machine. And it's an example of a really couple interesting phenomena. So first off, it's all about equilibria. So notice, oh shit, let me get it right back there. Okay, so right now it is at rest. It is at equilibrium. But this is an unstable equilibrium because the slightest nudge sends it careening down to this other. Now it's in a stable equilibrium. The parameter is what I'm doing with this little rubber band at the bottom. And I don't know if you can see it, there's a weird little like diamond-y shape. Can you kind of see that at the bottom? Weird little, and so that's a region where some really interesting behavior happens. And what Zeeman, the mathematician who created this, calls a catastrophe. So notice how it's pretty stable, and it's responding, like little movements here respond or correspond to smooth movements on the disk. So and for the most part, that is the case. But the minute I move it across this region, it becomes unstable and does these quick things called catastrophes. So you can imagine that if you were an engineer and you had something that would respond that way, that could be terrible, unless it's like a mousetrap or something you're building. But if you're building something that's supposed to be a stable structure, having moments like that, and this whole region, so this whole region is the region of jumps and hysteresis is like the fancy physical name for it. So anyway, I brought this in for that class. I thought I'd show you all. You can use calculus to understand what's happening there. And that's the cool part. You need a little physics. Always gets weird. Okay, hold on, let me get this out. I don't need any more caffeine. But let's get rolling. So I got two examples to start with, really. And then we'll get busy. The first example, so remember we were talking about partial fractions. And so let's say I've got this integral of x cubed plus 2x minus 3 all over this polynomial, and I'm going to we won't prefactor it. What the hell, will be really bold. So cool. So I've got this rational function, and a rational function is a function that's a ratio of two polynomials. So there's a poly on top and a poly on the bottom. That's just what the definition is. And that's what partial fractions is for. Anytime you've got a rational function and you see that the denominator can be factored, that's the key. If the denominator can be factored into simpler terms, this is the procedure for you. So one thing to note here is that the degree of the numerator is 3, degree of the denominator is 2. This is something we can't do yet. So partial fractions, let's talk about that. Partial fractions has kind of a flow to it, and we talked about some of the basics yesterday. There's one more basic we're going to talk about today, but it requires that the degree of the numerator is less than the degree of the denominator, strictly less. So even if this one down here had been third degree, I still am not quite ready to do partial fractions. I've got to do one thing first. If you have, so I'm giving you algorithms, the CS people might be happy with this, but these algorithms work good for our minds anyway. So if the degree of the numerator is at least the degree of the denominator, like here, we first use long division of polynomials. So I want to review that quickly for you, just how that works. Because it's kind of cool. I always thought it was really fun. Hopefully you can see that the bottom could be factored into x minus 3 times x minus 2. And if you didn't, maybe now you do. But I want to leave it unfactored for this. So for this procedure, have everything unfactored. For this. Okey-doke, cool. So I'm going to do this long division. I'm going to divide x squared minus 5x plus 6 into this thing here, which seems to be missing at least one of the terms. So you always want to have a descent of powers and have everything accounted for. So put placeholders in. Notice I put in that 0x squared to keep the space for x squareds in here. And then I copy the rest plus 2x minus 3. Everybody okay on light? Well, good on light? Anybody need more light? I can pop some up here. Maybe a little bit.
Maybe just in the front.
Yeah, absolutely.
Yeah.
Yeah, kind of. It's not the greatest either, but it helps. Okay. So the way this works is work with the leading terms. Always work with this highest power term here into the current highest power term over here. I'm not really looking at the rest of this, and so the question becomes, what do I have to multiply x squared by to get x cubed? And the answer is what? X, beautiful. So I put an x on top. I'm not thinking about this stuff, but now I'm going to see what the result, bless you, if I multiply this x times this whole thing. So that becomes x cubed minus 5x squared minus 6x. And then I'm going to subtract down. And this better cancel, otherwise I don't really understand what I'm doing because I put something up there that didn't cancel this thing out. So that piece is gonna die. Be careful with the double minuses. This becomes positive 5x squared. This becomes positive 8x and then a minus 3.
I think it's supposed to be 6x.
6.
It says a 6. Am I stupid? It says a 6 up there and you wrote an 8.
Yes, because I'm adding these two
duh.
here.
Thank you.
That's okay. And you're not stupid no matter what. There's no way you're stupid, my friend. You're very smart.
Shouldn't it be 6x though? Not negative 6x?
Now that I agree with, for sure. And maybe that's what you So, yes, I do agree with that. So that's a negative 4. Thank you. Yeah, I didn't copy the sign properly. It was like, well, I wasn't on the ball. So I think this looks okay now. You'll let me know. I trust you to let me know. Cool. So now I move to this. This is my new focus. What do I have to multiply x squared by to get 5x squared? Just a 5, yeah. And then I do that. So I get 5x squared minus 25x plus 30. I subtract down, dead. This becomes 21x minus 33. Now I'm done with the long division process. This can't go into this because the x squared would need like a negative power to do so. So at this point, I'm pretty much done, except I still have to do some partial fractions. So what this means is that this expression here, bless you, or whatever is called for in that circumstance, is equal to x plus 5 plus the remainder, 21x minus 33, over the original. And I'm going to factor it now, because I'm going to use that factorization for partial fractions. Does that sound okay? Yeah, oh yeah. Okay.
Is the factor supposed to be x minus
It sure
2, x
is,
minus
thanks.
2?
Thank you. Yeah, absolutely. Indeed. I said it once properly, so you know that I'm not completely out of the blue here. Any other questions or comments on that? Okay, cool. So partial fractions on this piece now, because the degree is 1 on top, degree is 2 on the bottom. So for this one, we're going to use par frac. And so I do the setup. And don't skip this setup, and because a lot of folks try to do stuff in their heads, and you can do a lot of things in your heads, but there's gonna come a day where you're gonna do something like I did and mistake something in your head. So this is helping us out here, especially to, like, I can't do these in my head. Maybe you can, that's possible. So then I flatten it out, multiply through by the denominator. Pick some nice values, x equals 2 and x equals 3. So I'm gonna let x equal 2, and then that gives me 42 minus 33, so 9, equals dead, and then negative 5, or no, negative 1b, that's nice. That's really cool. So b is negative 9, and then I'm gonna let x equal 3, and on the left, I guess that's just 21 more than this, so 30. Equals dead, b is dead, a is 1. Holy shit, that is nice. That's pretty good given I just made this up. I am pleased with myself. So destruction is sure to follow. Any questions on this? Looking good. Now we can wrap it up. We just rewrite our problem. So this, after the partial fractions, becomes integral x plus 5 plus 30 over, what was my, x minus 3, minus 9 over x minus 2 dx. Great thing to keep in mind is that integrals that look like this are just natural logs. There's a nice quick rule. And if you did the substitution, you would see that. If there was any other number besides 1 in front of that x, I'd have a factor out in front, but we don't have that right now. And this is the form a lot of things will take. So this becomes 1/2 x squared plus 5x plus 30 log x minus 3 minus 9 log x minus 2 plus c. And I rocked it out. Questions or corrections? Appreciate the corrections. When people correct me, I know they're like here.
Can you
They're checked in.
explain the 1/2 x squared plus 5x, just where that came from?
Yes, so that came from here. So if you this is power rule, this is x.
Oh, right, because you still have to take the integer.
Yes,
Okay, got it.
exactly. Yep. Other clarifications?
Just one.
Yeah.
So it always has to be the absolute value of the natural log, right?
It's always safer to keep that way. Yes.
Okay.
Yes. If there's something special that you know, like for example, Abraham, if this had been like, if I had natural log of x squared plus 3, I know that this can't be negative. That's always greater than or equal to 3, in fact. So then in those cases, I can just strip that off. But in general, it can't hurt. Okay, one last example, then we'll be able to rock out on that web work. So, and then next Monday, I'll be telling you about exam 1, which still is tentatively a week from this coming Monday. we'll see. We might have to move to Wednesday. It will be no later than Wednesday. And I'll let you know all that on Monday. Okay, so, next example. I've got in the bottom x squared plus 5 times x minus 3. So that's a cubic. And then on top, let's just say I have x squared minus 1. Yes. So luckily, no long division is needed because I've got a second degree on top, third degree in the bottom, effectively. But I have this thing here. This is irreducible over the real numbers. It has a factorization if we allow complex values in here. And I mean, I could factor it as like the difference of two squares, but I need an I in there. And we don't do that in this class. So if I'm allowed to use the square root of -1, I could factor it. But we don't want to go there. Like I said, I'll sell my class this fall again, MT480. Calculus with imaginary numbers. Okay, so enough hawking my wares. Let's talk about how to do this. So no long division needed. The setup is a little different. So the setup is going to be x squared minus 1 on top, and then this factor just stays as a factor itself, but we're going to do something different with it. So it gets its own term, this one gets its own term. This is just going to have a constant on top. The rule is the thing on top needs to be 1 degree less than the denominator. So here I would just put a C, because that's degree 1 on the bottom and degree 0 on top, right? There's an x to the 0 hidden in there. But this one I need a first degree arbitrary, so I'm going to put ax plus b on top. So just the little note here is that in setup, the fraction tops, I guess they're called numerators, fraction tops must be 1 degree less than the denominator degree. Other than that, it's the same. Oh, yeah.
So does this only apply for like irreducible things like that?
No, it does not.
Because we
in
went
fact.
over like x plus 1 squared yesterday, but that.
So that one came prefactored, right? So when we had this, that was prefactored, and that one would still, I would still put 2 terms for this. So this one I would have for this, and then I would just do this, because really what it's about is what's inside these parentheses here that matters to us. But if I had a polynomial I didn't want to factor, and I think you could do this one that way. I think if you had like x squared plus 2x plus 1 and you put this on top, I think that would probably work out. But I think it might be more work. I'm not sure. I think this ends up with a prettier path forward. And then you still have to factor this thing to do the integration anyway. So, yeah.
Okay.
So for repeated factors, I'm going to still recommend this. But like, let's say I had a polynomial that I just didn't feel like factoring, like that, even though that's a pretty easy one. I could do this on top and be cool. I'll still have to freaking factor it at the end. And like, honestly, integrating this is really painful. Integrating this and this, something over x plus 1, that's cake, right? So I think for the ease of, only do this when it's an irreducible, for your health and well-being. Good question, awesome question. Any others on this, like the setup? I want to solve this just and then be done. So I'm going to flatten this. And I get x squared minus 1 equals ax plus b quantity times x minus 3 plus, And then I'm gonna, this should say plus, I don't know why I put minus there. Some half-assed plusery. So then I've got c times x squared plus 5 here. All right, so picking values. There's less good values to pick when you have an irreducible, but you've always got some good, sweet values, good values. When you don't have, like 3 is obviously we're gonna go with, and that's gonna give us c immediately. But other good values are 0, 1, minus 1. Oh, you know, just the sweetest fruits that have been fermenting on the ground around us. Those are great. Get a little drunk off how powerful they are. So we've got x equals 3 first. And that's gonna give me an 8 equals 3a plus b. Oh, what, I don't care, times 0. I'll just freaking write it out. I picked it so this would die. And then here we've got 14c. So c equals 8/14 or 4/7 if we're gonna simplify. Let's simplify. Less digits to carry around. One less digit. So that, now I've got to pick some other values. I'm definitely going for x equals 0. And in fact, I have to pick 2 new values because this has something we haven't seen yet, I think, but maybe not. Let's try this. Let's let x equals 0. And then I get -1 equals b. So I think actually, I think we're gonna be, no, good. This does have what I wanted. So I've got b times -3 plus 5c. Oh shit. Do you see that I have b now? Because I know c. So since I know c, I could rock this out. Let's actually just go for it. Since c equals 4/7, we get -1 equals -3b plus 27. So that tells me that -3b equals -27/7. And this is getting weird, but b equals 27/21. Hey, again, you do not guess shit like this. Maybe Euler did. Baby Euler was guessing these when he just was in the crib, but for us, it's not much more work. So I'm going to put in -1, and on the left, I'm going to get a 0. I guess I could have put in, why am I putting in -1? What a weirdo. I'm going to put in +1, that's silliness. So I get 0 on the left, but then life becomes easier on the right. I've got a times 1 plus b times -2 plus c times 6. I know a, or excuse me, I know b, I know c, so now I know a. So use a equals 4/7, b equals 27/21, and we get 0 equals,
Should be C equals,
thank you so much.
equals 4/7, not that one.
Yes, oh,
B equals 27/21, you put A equals 4/7.
oh, thank you, got it, thank you, beautiful. Really important, thank you. So this was right, okay. So plugging in, I'm actually looking for A, so I'm gonna get -2a minus 2 times b plus 6 times c, and then I can get a from this, and do we care? I don't care. Like, you know, and so a equals something. Oh shit, I'll do it. No, I'll do it, because I want to finish the problem. So I'm going to move the 2a over here, and then this becomes -54/21 plus 24/7. And so that's actually, 3 of those is 72. So that's -54 plus 72 over 21 equals 2a. So a equals, oh gosh, 18, thank you. 18/42, because I divided by the 2 also. Is that okay? We're good? Okay, awesome. So our final answer is that this integral, instead of doing this integral, we're gonna do this integral. It's gonna be 18/42 x plus b is 27/21, and that's all over x squared plus 5. We will probably end up breaking that apart in a minute, but let's just go with the flow, and then c is 4/7. Questions, comments, size, T, L. Okie doke. I'm gonna get rid of this. And now I want to rock this out, and this is easy. If we keep in mind arctangent form. So with these, a lot of times you're gonna see this form. And that is an arctan. And here we have that, u is x, a is square root of 5. To get that, notice that this is square root of 5 squared. So, first I'm gonna break this apart. This is gonna be, I'm gonna do this in 3 different integrals. This is 18/42 times x over x squared plus 5. That's gonna be a natural log. Can you see that? That's a natural log form, because if u is the bottom, 2x will be the top. We just need a tweak. So that'll be a natural log form. This next one will be, wait, what am I doing? Bro, okay, so 27/21, 1 over x squared plus 5. There's our arctan. And then finally, we've got a natural log as well here.
This should be plus though, for 27.
Oh,
Yeah,
oh, is that a plus?
Yeah.
Thank you, thank you. Yes, good call. Solid. Many thanks. And so, okay, cool. So this is a natural log. I'm gonna speed through this just a bit because you've seen a bunch of these so far. 2x dx. So if I solve for dx, I get a 2 in the bottom. So another 2 comes out in front here, and this becomes 18/84. Yes, I could have made it 9 on top, but I didn't. Natural log of x squared plus 5. So Abraham, here's one where I could get rid of the absolute values if I chose. And then, but who cares, you know, that number out in front, nothing wrong with that number. Nothing wrong with that 27/21, even though it can be simplified. I'm gonna use that log, that tan form with a equals square root of 5. So I pop a square root of 5 in the bottom here. And then I put arctan of x over root of 5 here. And now, see, we're done pretty much. Then 4/7 log x minus 3. Can't remove the absolute values there. There's work to be done if we want, but that'll get web work happy. Yeah.
In the section with the arctan, should the numerator be 27?
Did I copy? Yes, thank you. Otherwise, what the hell am I writing that for? Yeah, good one. Thank you. Appreciate it. Appreciate it any time you help me, help you, help everyone else. We good? Okay, those are the 2 techniques that we hadn't talked about. They will clearly appear on the web work. So let's get rolling and work on that. Let's start on it. It should be open already. We've got a good half hour. So it's that you can actually do that in the future, like if you want, you know, you can always, I want to help you with your anti-technology goals, so.
You told me I could submit this if I wanted.
What's that?
You told me I could turn this into if I wanted. Is that what you're saying?
No, I'm not telling you that.
Okay.
No. I've done my part.
That's what I do.
Yeah, I'll come around and consult.
gonna run to the restroom, I'll be right back.
Okay. Got my mouth full of stuff, so I'll let you do the talking first.
So for setting this one up, is this kind of on the right track?
That's great. That's beautiful. Yep.
So I'm like supposed to have it A and B and then. set
Mm-hmm.
over.
Yeah, this one's nice and straightforward. Yep. A over whichever you want, B over the other.
And then set X equal to make it.
Well,
0.
first flatten it. So let's write it all
Oh,
out.
okay, yeah.
Write it all out, yes. Remember, we're gonna write more.
Yeah, yeah, yeah.
That's good. I was just kidding. I was like double checking that I was reading that right. So Cam, I gotta come check on you because we might have to talk as a group about what you're doing there. We'll see. Just a refresher, but. Oh, you're still getting there? Yeah, okay. Keep cruising. Let me know when you get your final, because I think what's gonna happen is you can only knock out 2 of these with good values, and then you're gonna get 2 equations and 2 unknowns. Okay. I think so, but let me know when you get to that point. We'll talk. Yeah, you just see what you're doing. You're the same one. Awesome. Cool. Which one is it?
Number 2.
Okay. Right up front. Right up there. Make my life so good. Make my life sweet. What is the original numerator power? Is it 4?
2. It's x.
Oh, sorry, the denominator.
Oh, yeah, it's x times x minus 2 cubed.
Okay, cool. This one actually, that's not a good example. Why did it make my life so much harder than it needed to be? Fix that up. No, that's better. Just real quick on number 2, which you're either at or you will be there shortly. We've got an integral like this. This is like, I guess, one more thing that we do need to talk about. So the setup, remember how when you have repeated factors, you're going to account for the power you're given and all the lesser powers as possible fractions that contributed to this one. And then I've got 3 for this, and then I've got 1 for the x. Flatten it out, boom, got that. Be real careful with the flattening. It's easy to screw up with the powers or the terms in general. Only 2 good values, one that kills this and one that kills x. When x equals 1, I get 2 equals C. Yay, amazing. When x equals 0, I get 1 equals negative D. Pretty damn amazing also. Not quite right there. I got 1 equal negative D. I had to think for a second. Now, I don't have any other good values for x. So I'm gonna pick wisely. First off, I'm gonna pick a -1 for x. That's always a good one. But another sweet value would be 2. Because 2 would turn all these factors into 1s. So you see that? Like I can choose wisely. I don't get the ultimate, pinnacle of sweet values, but I can approximate sweetness with the right choices. So let's let x equal 2 and just see how lovely that turns out. I get 5 equals a times 2, because all the x minus 1s become 1. So this is 2a plus 2b plus 2c. Oh, how nice is that, right? Plus 2d, oh no. Yes, 2d, what the hell? That's amazing. Cool. X equals -1's my other choice. There might be, I don't think there's anything else that's that good. So that we get 2 equals, now be really careful. The x minus 1 becomes -2. So I got -2 squared times a negative, so that becomes -4a. And then that one becomes plus 2b. And then that becomes minus c. And we're almost to the point I really want to make, so minus 8d. So how do you find a and b? Step 1 would be plug in what's known and at least use that information. So I'm going to take these 2 values to simplify these, but they're not going to do everything here. So I'm going to use c equals 2 and d equals -1. And what I'm going to get is 2 equations. So I'm going to get 5 equals 2a plus 2b, and then 2c will be 4. 2d will be -2. And then the second equation becomes 2 equals 4a plus 2b minus the c, which is 2 minus 8d, which becomes plus 8. So let's simplify one more time. This is a 2, I'm gonna bring it over here, so I've got 3 equals 2a plus 2b, and then this one becomes, this is a 6, move it over here, -4 equals 4a plus 2b. Any suggestions on what we could do here to find a and b? Yeah, yeah.
You could use algebra to make b in terms of a, for example.
Oh yeah, so that's a great option. I could take one of these equations and say b equals, like this one here, b equals half of 3 minus 2a. Awesome, can do that. Any other suggestions? What other ways?
Substitution.
What was that? Sorry.
We can multiply the first function by -1 and then add it to the second function.
Yeah, beautiful. So I can also combine the equations directly. That's called elimination of variables. And so I can just take this top one and subtract off the bottom one. And that kills the b's, and I know the a's immediately. So let's just do that. Now here I get 7 equals -2a. So a is -7/2. And now I can either go back and do that with the others, or just plug this into one of these. And let's just do that. So let's plug into 3 equals 2a plus 2b. That's a 2. We better watch it. I got 7s floating around also. So we get 3 equals -14/2 plus 2b. And b equals blah. Nobody gives a shit because it's not one of your problems. And then once I've got that, just plug those back in and log form, power rule. Easy. Okay, that should keep you rolling. Just be careful. Breathe easy.
Probably you need absolute value, Sophie.
Oh, probably.
Let's try it. Let's just see if that's what it wants.
Can you do absolute value with this?
Yeah, shift.
Oh, is it this one?
That one, yeah. Shift backslash.
Whoa,
There you go.
okay. Thank you.
You're welcome.
Okay, let's take a look here. Oh, that's weird. So, okay. Just check, I'm just gonna go through like certain principles here and check this. So first we got x equals -1. That gives you 0. Zero, cool. And that's cool, you just don't need any of those, so then, x equals 0. -2. There's d, cool, got d. And then you went for x equals 1, so x equals 1, maybe this. Okay. Okay. So then this is actually a positive 16, or negative 16, so we put that over here. So where did you get, you need one more equation, that's the problem. So you're actually taking what you've solved and putting it back into this original equation, and it's just
Got
got
brand
brand
new.
true.
Okay.
So pick one more value, and then use those to, take what you've done there and put that into the other show. Yeah.
You're doing good, Becky.
Thanks.
I'm not sure what's going on. So first it said I had a domain there, so I had an absolute.
Yeah.
Let's take a look. Let's see. So just a quick tip, and this isn't the problem, but you don't need those parentheses as well. You can actually just use the absolute values as parentheses. I don't think, let's check first to see what you got going on here, so. Okay. Your factorization is incorrect. That's the problem. So, so you were claiming from this that x minus 3 times x minus 1 is that.
Okay.
Let's check that out. What you got here? What's this you're doing? This is interesting. You have to you do it and then tell me what you're doing.
Okay, so AC, B, and over here, factors of B to give you AC.
Yes.
So -3, -1, minus -x.
Okay.
And it might be factors of,
Yeah, it's not working right. I think it's the other way because your L, you know, when you do a FOIL, your L would be -3 where you do it.
All right, bye folks. So real quick, just real quick, on Monday, we won't be working, we're gonna be talking about one new thing, so have questions ready, that's all. Just have questions ready on Monday, and I'll be right there.
see you later. Does that look better?
That looks way better.
Awesome.
Yeah.
Try that, I think that's the main problem we got here. Yes.
Did I do anything wrong here? Well, let's take a look. That is the right factorization. That is. So what's your setup, Gabe? What is it though? What is it? What are you claiming this equals? I just gotta know. So you've got this equals A over something plus B over something else. Tell me what those two things are. So what's the A over?
So, well, I set them equal to, or I gave them common denominators. So that's how.
You're skipping this step though. That's all I'm saying.
Okay.
I want you to write this for your safety's sake. And all part of our whole new 2023 is the year we write more shit.
Yeah.
My Sophie. So, like this, and then you came here, because it just helps you debug what might have gone wrong. So, okay, so this is great though. I knew what you were thinking, I just wanted you to write it.
Cool,
Yeah. Okay, so then you picked x equals 1, and you got 9, negative 9b equals 18, so b equals negative 2. It looks great. And then you put x equal negative 8. And that's, oh gosh, that's negative 48, so negative 36, yep. Equals, so this should have been a negative 9.
Did I just do my
You did some bad adding. That should be a negative 9 right there. That's gonna change everything.
Cool, thank you.
You're welcome.
Oh, yeah.
Yeah, and it works out.